Hi everyone, Dr. C. Let's just get started with a quick pre-lecture. You probably don't remember, but when we covered thermodynamics early in the semester, we skipped one section of the chapter, and that was a section that related thermodynamics, in particular delta G, the free energy change. So bringing back some memories from the start of the semester, and the equilibrium constant, K. Now, we had not covered equilibrium at that point, so we really couldn't cover that section yet. All right. So now we're going to do so very quickly. Just look at a couple of quick equations from that section. One of them looks like this. Okay. Now you'll notice there are two different delta G's. This is the standard state delta G, where if you have gases, they're at a pressure of 1 atmosphere. If you have solutions, they're typically at 1 molar. Temperatures typically, or the solutions are at 1 molar. Temperature is typically 25 Celsius. This is delta G under the non-standard conditions, or non-standard state conditions, but let's just say non-standard conditions for now. Okay, so they are different. Delta G is actually more universal. The standard state delta G is, only has specific pressures and concentrations, and once the reaction starts running, you're no longer at standard state. Okay, we'll talk about that more. R is the gas constant with units of energy, so we'll look at that in a minute. Temperature in Kelvin, and Q, you probably remember Q as the reaction quotient. Okay, calculated just like K, except you're plugging in initial concentrations or pressures. All right, so there we go. Nice equation. We're going to use this in the problem too, but for now we're going to modify this equation even further. And you may remember that at equilibrium, delta G is equal to 0. So delta G, the non-standard delta G, and we'll come back to the distinction here, tells us spontaneity. Is it spontaneous in the forward direction? Is it spontaneous in the reverse direction? At equilibrium, both directions are equally favorable, right? Because at equilibrium, the rate of the forward direction equals the rate of the reverse. That's why delta G is 0. So we can plug in to this above equation. So plug delta G into 0 in the top equation. And if we're at equilibrium, what does Q equal? At equilibrium, Q is K, the equilibrium constant. And if we rearrange this a little bit, delta G is minus, so we have to bring one over, minus RT ln K. All right, and that's a very nice, simple equation relating the free energy change and the equilibrium constant. All right, so let's look at the problem. I'm going to have to scroll back up so that I can actually see the numbers. All right, does anybody remember how to calculate delta G from delta H and delta S? Yeah, so this is good review. We're getting close to the final exam. It's been a long time since we've looked at thermodynamics or talked about free energy change. Remember, free energy change overall is chemical potential. It kind of tells us, what direction of a reaction is favored based on the chemical potential of the reaction. Well, you might remember that we can calculate delta G from delta H and delta S. All right. Now, typically we calculate delta G in kilojoules. I'm going to calculate in joules, and I'll tell you why, because it's going to need to be in joules for our next calculation. So let's go ahead and get this in joules. Delta G, negative 1652 times 10 to the third joules, so I've converted that. Temperature, 25 Celsius, 298 Kelvin, and our delta S is negative 543 joules per Kelvin. Okay. And let me pause first. No, I don't have to pause. My calculator's right here. See what we get here. Watch this double negative sign here. All right, let's do this in scientific notation. I end up with a delta G of negative 1.49 times 10 to the 6th joules. Okay? Now, the reason why I calculated that in joules is because my R, my gas constant, is in joules. It'll just make it easier to do the next part of this calculation. All right. So one thing when we were doing the thermodynamics chapter, we did not distinguish between these two delta G's. Okay, and I kind of did that intentionally because we didn't really have the information that we have now. Turns out the non-standard delta G is the one that tells us spontaneity. Is it spontaneous in the forward direction or reverse? What this delta G really tells us is what is favored at equilibrium. Are products favored at equilibrium, or are reactants favored at equilibrium? Or we could say, so let's leave it at that. So this would tell us negative delta G, products are favored at equilibrium. Okay? And that's a little bit different, and we'll make that distinction in the next problem of the difference between spontaneity and then saying products are favored at equilibrium. There is a difference there, and you might not quite have that down yet, and it's understandable, but we'll look at another problem and it'll make that clear what the difference is. Now, if products are favored at equilibrium, what do you know about your equilibrium constant? Yeah, it should be large. Okay, mostly products, large K, products over reactants. So let's see if that is the case. Our delta G here, negative, tells us products are favored at equilibrium. Let's see if we get that same information from our equilibrium constant. Okay, R, this is energy, free energy, so we need the R with units of energy, joules per mole Kelvin. Boy, I did not leave myself enough room, did I? It's just right below here. Temperature 298 Kelvin. Natural log of the equilibrium constant. Okay, negatives are going to cancel out there. And we should end up with a natural log of the equilibrium constant is about, let me get the couple more sig figs, 601.47. Now, a lot of calculators will do this. You have to have a display that goes past 10 to the 99th power. So if you have a graphing calculator, it will probably do this. If you don't have a graphing calculator, your calculator probably maxes out at 10 to the 99th power, and you will not be able to get an answer here. But we do have to go e raised to the x to solve this. My calculator will not do this calculation, but we can break this down to this. And I won't do this to you on an exam, although when I was an undergrad and taking my Gen Chem course, my chemistry professor in college did this to us, and almost everybody missed this problem. Because everybody's like, it gives you an overflow error or gives something on your calculator. But when we multiply, we add the exponent. So 200 plus 200 plus 201.47 adds up to that 601. And now we can do each of these separately. This is 3.143 times 10 to the 87th. And e to the 200 power, 7.226 times 10 to the 86th. And we have that twice. All right, we're still not done. And again, I wouldn't do this math to you on an exam or the final exam or anything like that, but it's kind of instructive to see. Let's multiply the first parts of the number. And so multiplying the first parts of the number, we get 164.1 or so times 10. And when we multiply, we add the exponents. So add 87 and 86 and 86. and that's to the 259th power. We could leave it like that. If we want to get our scientific notation as a number, and I don't even know, I think we have, let's see how many sig figs we have. It looks like we have 3. So 1.64 times 10. So since I decrease this by 2 powers of 10, I have to increase this by 2 powers of 10. 10 to the 261st. Wow. Okay. A lot of stuff there. Didn't want to get bogged down in the math. What I really want to focus on, though, is our delta G being negative, our delta G standard state being negative, tells us products are favored at equilibrium. Does our equilibrium constant tell us the same thing? Yes. Okay, very, very large K, almost exclusively products at equilibrium. Okay, now hang with me. I think we've been at this for about 10 minutes. The next 2 problems will be relatively quick. The first one, part A, will be really, really quick. Okay, so again, standard state delta G tells us whether products or reactants are favored at equilibrium. Negative, products are favored. Positive delta G standard, reactants are favored. Our equilibrium constant tells us the same thing. A large K, product favored. Small k, reactant favored. Those will go together. All right, so let's go down to number 2. We are given, and let me get on the next page so I can get all this to right together. All right, we are given the standard state delta G. It is negative, so that tells us that products are favored at equilibrium. Okay? Now, the question is, predict the direction each will shift to reach equilibrium. All right? Now, the first one, kind of tricky. Look at what all the pressures are. 1 atmosphere. These are standard state conditions. Okay? So we're already at standard conditions. We know that products are favored. Okay? So this is going to go, so in this case, our delta G is equal to our delta G standard. So delta G being negative 33.3. This would be spontaneous. Oh, I'm sorry. Okay, so in this case, we're already at standard conditions. So our delta G is our standard delta G. We are spontaneous in the forward direction. Okay, now let's compare that to part B. You will notice we're starting with a lot of product and almost no reactant. Okay, so we're already starting out with mostly product. This reaction is product favored, but we'll see that maybe since we start with so much more product than reactant, it's actually going to still be spontaneous in the reverse direction. And this is where it's going to seem a little bit odd, so hang with me. So now, to get spontaneity, we need the non-standard delta G. That's the one that actually tells us spontaneity. Again, the standard state delta G tells us products are favored. In this case, negative, but it tells us what's favored at equilibrium. Okay, so there's the other equation we started with. Let's plug in. And I'm going to go to joules again because R is in joules. So negative 33.3 times 10 to the third joules. (25 Celsius, 298 Kelvin). Natural log of Q, products over reactants, raised to the power of the coefficients. So the first one is ammonia, but we have a coefficient of 2, so we have to square that. And then I probably didn't leave myself enough room here as normal. Let me erase this. So then for nitrogen, we have 0.001, and for hydrogen, we have 0.001 but that is cubed. All right, break out your calculator. You probably have it out already. Let's do the natural log term first. 5 squared, 25 in the numerator. Divide by, well, 0.001 and 0.001 cubed, or you could divide by 0.001 to the fourth. So this comes out to 2.5 times 10 to the 13th power. Now you take the natural log, multiply by 298, multiply by 8.314. And I end up with, I haven't finished yet, I'm going to still leave this negative 33.3 times 10 to the third joules plus 7.64 times 10 to the fourth joules. Okay, so we have a negative and a positive. And we end up overall positive 4.31 times 10 to the fourth joules. Okay. So, there you go. What does that tell you? We get a positive delta G. That means this is spontaneous in the reverse direction. All right, now that might seem odd. This reaction is product favored. Okay, but since we're starting with conditions where we have way more product than reactant and very small amount of reactant relative to product, at those conditions, this reaction is actually going to go in the reverse direction. We're still going to end up with more product than reactant, okay? But we're going to decrease product a little bit. We're going to increase reactant a little bit to reach equilibrium, okay? So we will talk about this a little bit more in class, the difference between delta G standard state and delta G non-standard, okay? But again, just to re-emphasize, delta G standard state with this little superscript 0, okay? That means, tells you whether reactants or products are favored at equilibrium. And let's just write this down so we have these written. So if we look at the standard state, if it's negative, products are favored. Okay? If that is positive, reactants favored at equilibrium. Okay? So that's going to directly tie to our equilibrium constant. Now, the non-standard delta G is the one that actually tells us spontaneity. Negative, spontaneous in the forward direction. I can spell delta G, non-standard positive, spontaneous in the reverse direction. All right, so that was a lot for today for this pre-lecture. We are coming close to the end of the semester, so I want to make sure that we do have enough time to spend with the last material. We still have about a half a chapter of electrochemistry to cover and about half a chapter of nuclear chemistry. So about one more chapter to do over the last 2 weeks. We should be fine, but this will help us make sure that we get there. We will start class on Tuesday. We will review this. Okay, so make sure if you have any questions on this, in these calculations, let me know. The equations aren't particularly difficult. I will give these to you, of course. But make sure you know how delta G standard and the equilibrium constant are related. And then you will also be given this equation. Okay, and make sure you know make sure you can plug in and solve, but also make sure you understand the difference between delta G non-standard and delta G standard state. Okay, I think that's enough for now. I will see you in class. Take care.